So today it's time to talk about sheaves.
Mm.
Okay. So before we can talk about sheaves, we have to talk about presheaves. So sheaves written Sheaves and presheaves, singular sheaf. One sheaf, two sheaves. Okay, we take X for now just a topological space, and tau of X, its topology, meaning all open sets. Yeah? So a presheaf and sheaves and presheaves are usually denoted with a cursive letter. So this would be a cursive F of Z modules is a map such that F of U is a Z module for each U in tau of X. So you can think of it as a map from open sets into Z modules, and such that every time you have an open subset of U, there exists a restriction map. So this is our UV, restriction from U to V, FU into FV. And this is a morphism of Z modules, satisfying that if U is equal to V, then you simply have the identity on that particular Z module. And we have the following composition rule as well. So U to W is the same as going VW composed U V whenever W is containing V is containing U. And this maps, the maps are UV are called restrictions, restriction maps. Okay. So for instance, what you might think about here, we're gonna have plenty of examples in a second, but what you should think about for now, it's simply take an open set, take all smooth functions on the set. And the restriction is the restriction. Here I define a presheaf of Z modules, but the objects can be anything. Objects can be anything, not just Z modules. But for us, when we say presheaf, we mean presheaf of Z modules. Yeah, so I defined a presheaf of Z modules in this way. Here, instead of Z modules, you can have other objects, other modules, even just groups or whatever. And but for now on, when I say let's take a presheaf, I always mean a presheaf of Z modules. Okay, unless noted otherwise. So basic examples. Say that if X is equal to C, we can take H cursive H, C infinity, the presheaf of bounded function, presheaf of bounded holomorphic functions. So H C infinity of U is simply by definition is the collection of all maps from U to C, which are holomorphic and bounded. So for instance, we know if U is the all of C, this is just C, yeah. You have only constants. Otherwise, you have a lot of maps. If you take any topological space, and the restriction, of course, here is the restriction, yeah. Then we have the so-called constant presheaf. C, a constant, C to mean that the constants are complex, such that this is simply C for every U in tau x. Yeah, and the restriction is, well, just an entity. Yeah, we just do any open set, we just assign C. Then if we take some points, P1, Pn in X, GC is the, so this is a cursive G, is the skyscraper presheaf, such that, so GC of U is just 0 if Pj is not in U for all J, and GC of U is C to the L, where L is just the cardinality of P1 Pn intersected U. So basically, over these points, you have a copy of C, but everywhere else, you just have nothing. Okay, in some sense. And now that we have this object, this presheaves, let's define what morphism of presheaf is. When you have objects, you also want morphisms. So we take two presheaves. On the same topological space X. And then a morphism H from F to G is a collection HU with U in the topology, such that when we, let's say, evaluate it on a particular open set, this is a morphism of the module. But we want something more, and that is that the restriction maps commute with this H. Okay. So another way to think about this is this presheaves are, well, functors from the topology, and you think the topology is a category where the arrows are the inclusions and the objects are the open sets into presheaves. Sorry, into Z modules. And when we have a morphism, if HU is injective for all U in the topology, F is a sub presheaf of G. Okay, so if you're set-wise, let's say set-wise injective, so simply FU is a submodule of GU every time for every U, then we say that f is a sub-presheaf of G. Okay. And just an observation. So a priori, maybe it's not immediate. So, but an isomorphism. So, when you are okay, now we are imagining this category where the objects are presheaves and the arrows are these morphisms, these collections of morphisms. So, what is an isomorphism of presheaves? Sorry, from F to G. So H from F to G is such that there exists an inverse, right? So this is just the definition of isomorphism in any category. But the compositions need to be the identity respectively, right? And composition, of course, means composition open set wise, and identity means identity open set wise. So in particular, this is equivalent to ask that for every open set, HU is an isomorphism. For all U in the topology. Okay, which this is not for, I mean, it's easy, but it's not for free. Let's say it's not the definition of isomorphism. This is just a consequence. Okay. Okay, so now it's time to define what a sheaf is. So we start with the presheaf. On a topological space X. And F is a sheaf if for any collection of sets here, such that U, I mean, maybe not such that, but with, U is defined this way, with U equal the union of these UIs. We have two properties, which we call S1 and S2 from sheaf 1 and sheaf 2. So if you have two elements here, such that they restrict to the same elements for each of these open sets, this is for every I, then they were actually the same. Okay, so if all restrictions are the same, so imagine that these UIs are covering you, and if all restrictions are the same, then they were actually the same in the first place. What S2 is that things glue. So what do I mean by this? If for every J there exists an Fj, such that if I restrict from Uj to Ui intersected Uj of Fj is the same as the restriction from Ui to Ui intersected Uj Fi. So what does this mean? It basically means on each of these open set, you have one of these elements, which think really much of functions. What you're saying is that in the intersections, they coincide. Yeah, the restrictions are the same. Then they can actually glue to a function on the old set. And this is for every ij. Okay. So we have this S1, which just means that if two things restrict to the same, then they are the same. So think in terms of functions, if two functions are locally the same, then they're the same. Well, this one, the second one is more so, yeah, if you have function here, a function here, and they're the same on the intersection, then you can actually, there exists a function which is on the union, basically, which restricts to those. And then we have some naturally definitions. So morphism here. So morphism of sheaves is just a morphism of presheaves. And a subsheaf is a sub presheaf that is also a sheaf. Yeah, so nothing fancy. So examples to see what we're dealing with. Well, first of all, we have what I was mentioning before, and that is the structure sheaf. Structure sheaf of a manifold. So in the case of a smooth manifold, it's the sheaf for smooth functions. In the case of a complex manifold, it's the sheaf for holomorphic functions. Yeah, we defined this at the beginning when we defined germs, if you remember. Then we have locally constant functions. Constant functions, Cx, such that Cx of u is a set of functions from u to C, but to C we put the discrete topology. So the only continuous functions into it are the ones which are constant on each connected component. Okay, I want to take a second here because here we have locally constant. Well, before when we're looking at presheaves, we had constants, right? And so let's say that your set U is just the union of two disjoint sets, okay? Then on here, you can put one constant and here another, right? And on the intersection, they restrict to the same thing simply because that's an empty requirement. So if we look at condition 2, yeah, this is I mean, if you take just two disjoint sets, and you put a function here and a function here, this is perfectly satisfied simply because it's an empty requirement. But then in the constant presheaf, you don't have an element on the union of the two, right? Because it cannot restrict to two different constants. Yeah, because this one also only has constants. Even if you have different connected component, must be constant. While the locally constant, of course, if you have two separate connected components, you can have a function which is one constant here and one constant here. As another example of these things, which like the difference between sheaves and presheaves, the presheaf of holomorphic and bounded function is not a sheaf on C. And to show this, let's just say, let's say our uj are simply the balls of radius j. Okay. And as fj of z, we just take the identity z. This is bounded on each uj, right? Because it's bounded by j. But you cannot find a function on the all of C. And because I think C has the union of these UJs, yeah? It's just a union of both. Such that if you restrict it, you get FJ of Z. Okay, simply because the identity function on the all of C is not bounded. Okay. Other sheaves. So if X and Y are topological spaces, we can a bit generalize this structure sheaves, then continuous functions from U to Y is a sheaf. Yeah. And so we saw examples of presheaves and of sheaves, and we saw examples of presheaves which are not sheaves because they don't satisfy S2. So now I want to show an example of a presheaf, which is not a sheaf because it doesn't satisfy S1. Okay, so to show that both things do something. And here the thing is very simple. Our topological space is just AB, so just 2 points with the discrete topology. And then we assign. Okay, so we define our sheaf A, presheaf A. So if the open set is just A, we put Z. If the open set is just B, we also put Z. And on the old set, we again put Z. So it's the constant shift Z. Yeah? But the restrictions we take, so it's not the constant shift. It looks like the constant shift Z, but in the constant shift, the restrictions are the identity maps. While here, as restrictions, we take the zero maps. So I only have to restrict from X to A and from X to P. And we just take to be the zero map. Isomorphism of Z modules, send everything to zero. That's always okay. And A is a presheaf because we have these restrictions. But it does not. But it does not satisfy S1. So this particular example does not satisfy S1. Why not? Well, because whatever two constants you take, whatever constant you take here, the restriction will be zero. But they don't necessarily come from the same object. Okay. So now I want to define something a bit more complex, which is related to what we did last week. So I'm going to start with, so now we kind of do something more complicated than Z modules. So we take R, cursive R, to be either a sheaf or a presheaf of commutative rings with unity rings. And F, presheaf or sheaf of abelian groups, in particular of Z modules on X. And we say that F is a sheaf of our modules. Well, I think you can guess it. If F of U is our U module, for each U, and every time you have V, which is contained in U, and alpha, an element in the ring, and V in FU. Just need to tell you how restrictions work on this. And the point is that they are compatible. So if I take the restriction from U to V in F of alpha times V, which is a well-defined element of FU, yeah, This is the same at restricting alpha in R and multiplying it. So this is happening, this multiplication now is happening in FV with the restriction of V respect to F. Okay. So you have this simple relationship that things work well, let's say. And let's give examples of this as well. Well, if M is a complex manifold, then the two structure sheaves so sorry, that's not what I meant. So if we have a complex manifold and we take OM as the sheaf of holomorphic functions, and smooth function into C, so this is the sheaf of smooth functions into C, so important is into C, then you see that the C infinity MC is a OM module. Yeah, for instance, if you multiply smooth function by holomorphic function, this is still a smooth function. Okay. Another example, we can take the presheaf of meromorphic functions and mx prime. Sorry, maybe instead of x, let's use m, because m is our manifold here. So m stands for meromorphic, the little m stands for the fact that we're in the complex manifold. The prime, we will find out in a moment, I mean, in a bit, why there is a prime here. It has to be with the fact that it's not a sheaf, but it's only presheaf. But we'll see all of that in due time. And what is this? Well, to every open set U, you assign the quotient OMX modulus U. Yeah. And this is happening when U is connected. Sorry, and with this I mean like the not the quotient as groups, but like the field. You know, every time you have a module, you can make with node zero divisors, you can make the field a field out of it. So this is field coming from yeah, this is not a quotient. So of course, holomorphic functions on connected sets have no zero divisors. Careful, because on disconnected sets, holomorphic functions do have zero divisors, but on connected sets we don't have them, so we define it like this. And if we have a disconnected set, so let's say U1 disconnected union U2, this is defined as M prime of U1 plus M prime M U2. Okay. So this might appear that it only works for finite unions, because I'm only telling you how it works for finite unions. But notice here I'm taking the sum, not the product. So this actually also works for infinite. You just take the infinite sum. So when we have, if you remember when we had, so all of this is somewhat related to bundles, vector bundles, as we'll see in a bit. And for bundles, so we want to like define notions which are somewhat similar. So now I want to define the restriction of a sheaf or a presheaf. So let's take a sheaf or presheaf on X and an open set. Then the restriction presheaf or sheaf. F restricted to U, that's how we write it, is such that F to U of V is simply F of V for V containing U. So this is now a sheaf on U. F restricted to U is simply a sheaf on U. Okay. No big. So there are kind of two parallels here. There is one which is more with vector bundles, particular sections of vector bundles, but again, this will come very soon. And then there's another aspect which is more to do with rings and how do rings behave. So now we'll go back to rings. So we take a manifold, we take a sheaf of commutative rings on M, and we take an integer M, and observe that the sheaf that sends U to R to the M of U, and with this I mean just the sum, M times, this is now a sheaf of R modules. It's a sheaf of R modules. And this is a very important sheaf in a sense, because this is called free sheaf. In the same as free modules are simply a direct sum, we call it a free sheaf. So if sheaf F, this is a cursive F, of R modules is isomorphic as sheaves to Rm, we say that F is a R free sheaf of rank M. Okay. And then we have the definition of locally free, which is actually more interesting for us. So a sheaf F of R modules is locally free if for every point in the manifold there exists a neighborhood of that point, NGH, such that if you restrict F to U, this is RU free. Okay? Which, careful, a priori, this is not the same as saying that F of U is the sum. Yeah, this is not the same. Okay. You want that for every subset of F, every subset V of U, F of V is the sum of RVs. And why did we stress? So these last three definitions, as I was telling you, they have to do a bit with the relationship, of course, between sheaves and rings, which is obvious because it's a sheaf of rings, and a bit of the relationship, which we didn't explore yet, between sheaves and vector bundles. So now this first proposition will actually give us this relationship. So we take a smooth manifold, and a vector bundle or this manifold of rank R, and we define the sheaf E, cursive E, that sends an open set to sections of the bundle over that open set. So these are sections of E restricted to U, basically. Okay. And this is a sheaf. I think it's clear why it's a sheaf. Oh, of course, each of this is a so it's a sheaf of R modules where R is the smooth functions. Yeah. And you see that if two things, we know that if two things are the same, then you can glue them together and things like that. So we know that S1 and S2 hold. Then E, so this is not just any sheaf, it's a locally free sheaf. So locally free sheaf of infinity M modules of rank R. So same rank. Not only this, we do have a vice versa. So given a locally free sheaf E of infinity M modules of fixed rank R, we can construct a bundle, a vector bundle E of rank R, such that E is its sheaf of sections. And for your more, this correspondence is bijective up to isomorphism. Yeah, so every bundle has its own sheaf of sections, and if the two bundles are isomorphic, then so are the sheaves, and vice versa. Okay, so time for the proof. So that is a sheaf. It's okay. No. So what we know is that this is a vector bundle, and so we take a trivializing atlas for it. And then we simply take, in each of this open sets, we take a basis of sections. Okay, so this is something we've done lots of times before. So EJ is the canonical base elements of R to the R, and this is simply the image under the trivialization map. Okay, so if we take an element here, so what I'm trying to prove is that E is locally free, yeah, of rank R. This is a section, so I can write it, since this is a basis, like this. And AJ here is just a smooth function on U alpha. Okay. And now I think it's pretty obvious what we want to do, because we define map from here to here. Send such a section here to the R tuple of smooth functions. Okay. So this is an isomorphism because these are unique. These are uniquely determined. So this is an isomorphism. So this means that E is locally free. Yeah. Because E U alpha is isomorphic to infinity U alpha, and U alphas cover everything. And if you shrink U alpha, you still get the same exact thing. So you get that the E restricted to U alpha is locally infinity M free. Vice versa. We take a locally free sheaf. Then what it means that there exists a covering U alpha of M such that E restricted to U alpha is free. So locally free means exactly this. So in particular, we have maps of sheaves phi alpha from E restricted to U alpha. This is an isomorphism into infinity M restricted to U alpha to the R. Okay, this is just a definition of locally free. And now what we want to do is define a bundle out of this. And it's not too hard once you have the structure, because we can take EJ as a map from M to R to the R. So this will basically be our basis, such that EJ of X is simply 0, 0, 1 at the jth path and then zeros again. So this is a function from M to R to the R. It's a smooth function. And in particular, so observe that E1 restricted to V, comma, comma, ER restricted to V are generators for this module. So it's infinity M V to the R for any V in M. Okay, so generate as a infinity MV module. So very simple. But now things are easy because we have this very nice elements, and we can define Vj alpha as the anti-image of Vj. No? And since this is an isomorphism, this also generate, sorry, Vr alpha V. So this generate EV for any V containing alpha. Okay. We have actually something additional. Furthermore, there are functions M alpha beta from U alpha intersected U beta into GL R R such that Vj alpha is simply sum from k equal 1 to R of mjk alpha beta bk beta whenever alpha intersected beta, sorry, U alpha intersected U beta is non-empty. So why is this? Well, of course, if you take V in, we'll say even equal to U alpha intersected U beta, you have two distinct sets of generators. One is V1 alpha, Vm alpha. Yeah. And the other one is V1 beta, Vr beta. So these are generators as generators not in a vector space sense, but in a C-infinity M module sense. Okay. So they're one the linear combination of the other, but the coefficients are not constants, they're functions. So this is what this M alpha beta JK comes from. You can just think that each of them is a smooth function. And then, of course, since they both generate, for every fixed P, let's say, for every fixed point in the manifold in V, what this ends up being a matrix needs to be non-singular. Okay? And this is what we have GLR. Otherwise, in principle, would just be R to the R times R to the R. No, R to the R squared, sorry. Just a R times R matrix. But then, since they both generate, it's non-singular at every point. And furthermore, so also, now this matrix M alpha beta satisfy cocycle identity. Satisfy cocycle identities. Yeah. Simply because, again, these are free generators, so there is no relationship between them. So even if you go back to A, then the product of these two matrices must be the identity. If you add the gamma, then you have this threefold three index relationship, etc., etc., etc. Okay. So that they find a vector bundle. And you're like, aha, okay, so this is the bundle E. This is not E, actually. E is the dual of this. So prove that the sheaf of sections of E, this is F star, is isomorphic to E. So what we started with. Yeah, and the reason we already saw it basically is that the transition functions are for coordinates, right? But here we're not doing transition for coordinates, we're doing transition for sections. So what you get is the inverse transpose matrix when you switch to coordinates. This is a standard thing in linear algebra. We already saw it when we were defining, in fact, the vector bundle, the dual of a vector bundle. We saw how the transition maps change, and they change as negative transpose. And this is pretty much the same. Okay, because also notice when we did the first direction, where is it? Here we have sections and we go to the coordinates, right? So this correspondence is with the coordinates, but this correspondence is not with coordinates, it's with sections. So this must be negative t. So this is the first exercise. There's another exercise in this proof, which is to prove that the relation is bijective. So this is equivalent to saying that if you have two sheaves which are isomorphic, then the corresponding vector bundles are isomorphic and vice versa. And if you look at the proof, you will see that the fact that we were using smooth functions instead of, for instance, holomorphic function doesn't really matter. So we have the same correspondence works between holomorphic vector bundles and locally free OM modules. Okay. Sorry, not modules, of course. Locally OM free, sorry. The right way to write is locally OM free sheaves. My bad. Okay. So here we have rings, right? And we have lots of rings. And in the past week, all we did with rings, well, not all we did, but important thing of what we did with rings was to understand direct limits of rings. And all of this was functional to what we're doing now. So if we take presheaf, be a presheaf on x, and we take x to be a point, then we take tau small x big X to be all open neighborhoods of X. So simply all open sets which contain this point. And this is a partially ordered directed system. With U is this weird less or equal than V, if and only if V is contained in U. Yeah, it's a directed system. Okay, of course, it's partially ordered, and it's a directed system because if you take any two sets, any two open sets, their intersection being non-empty, and that's important because X is in there, is greater than both of them because it's actually smaller. So it is a directed system. Hence, we can define direct limits. So the direct limit, which we call f small x, and u is from this directed system, is what we call the stalk of f at x. So what is an element here? So elements of fx are equivalence classes, equivalence class of A for A in fu for some u neighborhood of x. And we know that two classes are equivalent. So sorry, two elements are equivalent, so they're the same class. If and only if there exists another neighborhood of x such that B is represented in this neighborhood, and these two objects restrict to the same object for some other neighborhood. Okay. And so this should really make you think of germs of functions. Yeah, if our sheaf f is simply the structure sheaf of a manifold, then this is simply the germs at x. And in fact, we write instead of equivalence class of A, we write AX, just like you do for germs. Okay. And maybe one thing which is worth recalling is that if f is now a presheaf or a sheaf of R modules, then fx is itself a Rx module. This is a recall because we saw this for directed systems, RR directed system of R rings, right? So this F is, if F is a presheaf of R modules, in particular, this when we take only neighborhoods of a point, this is a directed system of R modules, where R is itself a sheaf. And so when you take the limit, you know that the limit is Rx module. And furthermore, if H is a morphism between sheaves or presheaves, then also the direct limit is well defined. And it's also morphism. Yeah? And here we have a theorem which gives us a relationship between properties of the morphism on the stalk and properties of the morphism between sheaves. So let's start with, again, a morphism between sheaves. Then HU is injective for all U in the topology, if and only if HX is injective for every point. And the same is true for isomorphisms. But it's not true for subjectivity. No? So if it's injective, if and only if injective, and injective and surjective, if and only if injective and surjective. But surjective alone doesn't work, and actually it's an example of that. So for what we know about direct limits, one direction is true. But this is then this also must be surjective. Huh? So this is just something we know from direct limits. The vice versa, we take x equals c, and as a morphism, take the derivation. Okay, that takes holomorphic functions and gives you another holomorphic function, f prime. Now you know that if U is simply connected, then this is surjective. Right? What it means is that on simply connected sets, every holomorphic function has a primitive. Okay, this we know. And since every point has a neighborhood basis of simply connected sets, you can simply take disks shrinking. Then the direct limit is surjective. Okay, and if this looks too much, I don't know, algebraic mumbo jumbo, just think about it more directly. You have um, a germ, yeah, and you can locally represent it by a function, and you can take this locally to be on a simply connected set. That's what it means. And so on this simply connected set, that represented it for the germ as a primitive. But now if you take the germ of that primitive, that would be a preimage. Okay. But of course, if you take another open set, which is not simply connected, for instance, C minus 1 point, this is not surjective. For instance, take the function 1 over x, 1 over z. So 1 over z is a holomorphic function c minus 0, and we know it does not have a primitive. Okay. So let's go back to the theorem and actually prove it. So proof. Okay, these directions are done. Simply, this is the property of direct limits. Yeah, as we said here, basically, it's the same concept. So if it's true for every open set, then in particular it's true on the stocks. So for the direct limit. But let's see the vice versa. So I start with injectivity and assume that hx is injective for every x in x. Take an open set and assume that we have A and B that map to the same object. So HUA is the same as HUB. Okay, so we're trying to prove it's injective, so we assume it's not. Or at least we have to prove just A equal B. In particular, what if you take, now if you look at this in the direct limit, what it means is that hx of ax is the same as hx of bx for every x in this particular open set. Yeah. So the germs, which I should not be allowed to call germs, are the same. Because the hx is injective. But what does it mean for this to be true for every point? It means that there exists a covering of U such that if we restrict to that covering, these are the same. Okay, because being having the same thing here means that locally there is a representative which is the same, and this locally is this uj. Okay, and the representative is of course just a restriction. But now by S1 sheaves, A is equal to B. So it's important that we're talking about sheaves and not just presheaves. Okay. So what about isomorphisms? So we know that HU is injective. We have to check surjectivity. We need to check surjectivity. And we already know that somewhere we actually have to use that HU is injective. We have to use it somewhere. So, well, let's just take an element here. Right. And we know that Hx by hypothesis is surjective because in fact it's an isomorphism. So for every x in U, there exists an Ax in the stock such that Hx of Ax is Bx. Okay. But again, we can having the same restriction, sorry, not restriction, having the same image in the stock is equivalent to say that there is a representative which is actually the same. So a local representative. So there exists a covering, and the elements in this covering, such as Aj, is sent to the restriction of B. Okay. So this is the same thing, but seen in some locally. Okay. And if two, so we have these AJs, which is nice, but what we need is an A. So an A which covers all of you. So the idea is to try to glue these AJs. So so using S2 for sheaves. So if this is non-empty, we can take a few restrictions. So basically what I'm doing here as I'm pre-composing with the restriction from uj to ui intersected uj, but then I'm allowed to switch because this is a morphism of sheaves. Okay, this one clear? How we got here? From here to here, you're just composing with this, and on this side then we switch, and on this side we know that the composition satisfies this. But now, since this map is injective, yeah, because we know by the first part, so we use HU injective. You see, they all go to the same element. This is the same as this. Yeah. Simply because they all go to the same thing, which is this one. So here I can put equal, and then here instead of J, I switch J and I. Okay. Okay, so now we can use S2. And finally, you find an element A in FU such that if you restrict it to each of these UJs, you get precisely AJ. Okay, so what I'm left to prove now is that the image of this A is exactly this B. Okay. And I cannot do it directly, but what I will do is take this. So I will prove that they're locally the same, and this means that they are the same by S1. So with this, which is equivalent to this, by how A is defined. Now you can switch these two. So on one side we have this, and on the other side we have that this was simply RU UJ of B, right? Yeah, we took AJ on purpose. Where was it? AJ, AJ, AJ. There it is, this one. Yeah. So we conclude that if you restrict B to UJ, is the same as restricting HU for A to J. So by S1, B, yes, HU of A. which concludes the proof. Okay, so you see that, I mean, of course, we have the example which tells us that surjectivity does not imply surjectivity. The surjectivity of the stalks does not imply surjectivity for every open set. But here we see how we really used injectivity, and is to really glue these things. Yeah, there's no difference between them. Like you have locally a pre-image, and then, okay, locally you have a pre-image. Then what? Well, if you can glue them together, then you have a pre-image on the bigger set, but you can only glue them together if you have injectivity. Okay, so far we made this distinction between sheaves and presheaves. And as we saw, it's an important distinction because we have these two extra properties. But the next proposition kind of tells us, not really, but that given stalks, there is only one sheaf that has the stalks, in some sense. So, but the way the proposition is given is that we take a presheaf, you look at the stalks of the presheaf, which are well defined, and then from those stalks you make a sheaf. So every presheaf can be extended somehow to sheaf. So I already gave an idea of the proof, but before the proof, let's just write down the theorem, otherwise it's a bit hard to follow. So we take a presheaf on X. Then there exists a F plus, a sheaf, and a map theta from F to F plus, which is a presheaf morphism. Presheaf morphism. Yeah. Which factors everything, basically. So every time you have a map phi from F into G, which is a presheaf morphism, presheaf morphism into a sheaf with G sheaf, there exists a phi plus from F plus into G. Now this is a sheaf morphism. Which factors? So phi is phi plus composed theta. Okay. And of course, this looks like some kind of factoring universal property thing. So we have unicity. So F plus theta is unique up to isomorphism. Okay. And so saying the proof kind of relies on stalks very heavily. Oh, sorry, there was an extra in the furthermore, unique up to morphism. And if you look at the theta x, so if you again restrict to the stalks, this is the identity map. So they're not only isomorphic, they're actually the same, and the induced map is the identity. So this is what I was trying to explain before, is that given some stalks, there is only one sheaf which has the stalks. So proof. So we want to just define this F plus and then see that it works. So we take U in here and we define F plus of U. A set of maps from U into the disjoint union for X in U of Fx. So simply to every point in U, you associate an element of the stalk such that, so now there's going to be some interesting thing. So f of x is an fx. So this looks like kind of sections, you know. But furthermore, if for every x in U, there exists a neighborhood of x and the G in the presheaf over V, such that the let's call it the germ of G at Y is exactly f of Y for every Y in V. Okay, what it means before we move forward. So just think that over every point, we're putting the stock of the presheaf. Okay, and we're taking kind of sections of this construction. But since here, like while in vector bundles, you have a notion of continuity, like, you know, this is all one object, and if you go from one fiber to the other, you know what it means to be continuous. You would just have a disjoint union. So we don't really have a notion of continuity. You're just putting over every point, you're just choosing one element. What this following condition, this extra condition, guarantees some kind of continuity. So it means that near every point, you represent, so it's not like every point has its own element, but every neighborhood has its own element. Yeah, so locally you're represented by just one element. Okay. So the annoying part here is to prove that this is a sheaf. With restrictions given by the restriction. Yeah, these are functions, so we can simply restrict them. And now I have also to define this theta. So this is a map between presheaves, so I have to define it on every open set. And what does it do? Well, it takes element f and sends it to what we call f plus of x, which is nothing but the germ of f itself. Yeah. So we send it to this element f plus. And now it's clear that the first furthermore, the second furthermore is clear. And that is that theta x is identity. Yeah, because when you take the limit here, what you get is from f, you get simply fx, right? And when you take the limit here, well, again, you get fx. Okay. So you can think of the diagram confused. You can think of this diagram. You have fu, you have f plus u, and here you have fx, and here you have f plus x, and you have theta. So here you have an element f. You have the corresponding element f plus, right? And when you go down here, of course, here you get fx just by definition. And here you get something which is this fx plus, but what is it? Well, this is just fx itself. So this is the identity map. Okay, so this was the furthermore, so definitely not the most important part. We have to show that this theta factors everything. So, blue pen. We take a map, which is a morphism of presheaves. Morphism of presheaves, but G is a sheaf. And how do we define phi plus? Well, we take an element, right? And the cool thing here is that since it's locally represented by one thing, there exists a covering and AJ is in this covering. So covering of you, of course. Such that f of y is precisely the germ of this AJ in the point y. Okay, so if you forget this J part, this is simply the definition, right? So this takes, we have f simply takes a point x and sends it to just some element in the stock, right? So this is the first part. Okay, you just take a point in you and you send it to some element in the stock. Okay, so you can think that like you send, oh sorry, you can think that in principle this would be f of y equal a little y. Okay, but a is not an element of fu. A is just a, like a by itself is nothing. You have ay, and this is an element of the stock, but otherwise a doesn't mean anything. But this extra condition guarantees that locally, so meaning we can find a cover, locally there is actually an element, oh sorry, this should be a uj. There is locally, there is one element which represents your a. Okay, so this is where this is coming from. And okay, we still have to define the image of this object. But now it's a bit easier because the idea is to simply now take the image. You saw locally this is represented by AJ. You take the image of the AJs and then you try to glue them together. So let's see if that works. So you can restrict from UJ to UJ intersected UK of phi UJ AJ. This is the same as this. UK UJ intersected UK UK AK. And of course, since G is a sheaf, so in particular it satisfies S2, there exists an element which restricted is precisely the image. So U to UJ of B is phi UJ of AJ. Okay. And this point, of course, we simply define phi U plus of F to be this B. Okay. So already from here, before we continue, you observe that this F plus compared to F, what does he have more? What is there more, right? Because we had a presheaf. We had a presheaf, so what is more here? And while in the original presheaf, you have this elements Fs, here you can take things which are locally, so this thing here, which are locally represented by elements of the presheaf. Okay, so the presheaf is just all these elements, and F plus is things which are locally part of the presheaf. Okay, so this is the idea behind this construction. And maybe a small observation here is that, yeah, if you take this composition, this is just phi of F. And the reason for this is because can take the AJs in the proof. Oops, AJ. We can simply take the restriction of F to UJ. So we don't have to take some random ones. We can simply take the specific ones. And this gives this equality. Okay. Uniqueness. Okay. Uniqueness. Actually, I'll do it in a separate page. More room. So, assuming that we have another pair. So we have a pair F tilde plus theta tilde have the same property. Same properties. Okay, but then if we take theta tilde, so theta tilde is a map, if you remember, from, so theta would be a map, where is it? Theta would be a map from the pre-sheaf into the new sheaf. So from F into F plus. Okay. But so I can put a plus on it. Okay. So this would be from F tilde, theta tilde would be from F tilde into F tilde into, sorry, into F plus. So theta tilde plus becomes a map from F tilde plus into F plus. And the same in the other way. Yeah. So these are well defined. And they satisfy these conditions. Okay, this is basically, I mean, is the proposition applied one time with phi equal theta tilde, and one time with theta and theta tilde switched. So we're assuming they have the same property. Okay, so now we do some extra compositions, and we get phi plus compose phi tilde plus compose theta is theta itself. So to achieve this, I am composing on the left by theta plus. See? So if I had theta plus here I get theta plus composed theta tilde, but this is theta. And I can do the same on the other side. So of course, everything is symmetric in theta tilde. So we have this. Now we take the direct limit. And what do we get? Okay, here we get theta plus x. Here we get theta tilde plus x. But then we know that the theta x and theta tilde x are just identity, correct? So this is the identity. I mean, not on x, it's identity on, it's identity on the correct domain, which would be f tilde x in this case. And the same is true for the other direction. Okay, but this simply tells us that theta tilde plus x, and of course also theta plus x, are isomorphisms on the stalks. Yeah. But luckily, we just proved that if a morphism between sheaves, and with the plus is a morphism between sheaves, are isomorphism on the stalks, then they're just isomorphisms. Okay. So this last part is nothing but taking compositions. It's really nothing fancy. While here, I understand this proof is involved. And it's really important to understand, I think, how this F plus comes to be. Especially, I mean, we will talk about this next time, but as a small spoiler, um, it has to do with what we did here, that surjectivity on the stalks does not imply surjectivity overall. This is linked somehow to the fact that the kernel of a morphism is in fact a sheaf, but the image of a morphism is not a sheaf. So when we want to talk about images of morphisms between sheaves, we don't actually take the image, but we take the sheaf associated to the image through this thing. So it's really important to understand what this is and what the elements of F plus are. And just to repeat it once again, I think the best intuition here is to think that you have a presheaf which has elements, and the elements of F plus are the ones which can be locally represented as elements of F. This is, I think, the most intuitive way I can give it. Okay. And then you have the beautiful theorem, which tells you that basically everything comes down to the stalks in the end. Okay, so this will be it for today. Is there any question?
No, not really. Okay.